Welcome to this CoBCoM lecture about adaptive phase correction for diffusion-weighted images. My name is Marco Pizzolato, and I've carried out the research work for this project together with Guillaume Gilbert, Jean-Philippe Tiran, Maxime Decoteau, and Rachid Derish. The talk I'm going to present is about the corresponding article published on NeuroImage. And here I would really like to focus on the two parts of this title. First, diffusion-weighted images, and I would like to talk about a bit what they are useful for, and the second part will be actually about adaptive phase correction for them. So the focus is on non-invasive brain imaging with magnetic resonance imaging, so MRI. And here we see a brain, and what we can do, for instance, with that is to reconstruct the 3D anatomical shape of the white matter structure. And here we see also other two projections of this three-dimensional procedure. However, we can do many other things with the use of diffusion information. Indeed, the key for this kind of processing is really the measurement of water diffusion. Water diffusion actually occurs at a micrometer scale, and in the brain live tissue, actually, it's hindered by the barriers of the so-called microstructure. So here we see some cells, and we can really see in the zoom that water particle can displace within, between, and actually across as well these barriers. So diffusion MRI or diffusion-weighted magnetic resonance imaging can really allow us to track the motion of water particles, and therefore can actually provide us with information about the microstructure itself. But what is this microstructure? Well, if we were to zoom in a specific point of the brain, like the red rectangle there, well, looking in, we will actually see that the microstructure is composed by several structures themselves, like axons, vessels, vacuoles, and cells, for instance. And so here we are zooming at 150 micrometers scale. This is synchrotron imaging. And now we can understand why diffusion is so important, because it actually occurs at the scale that is corresponding to the scale of these structures. So we can say that the microstructure determines the diffusion properties that we measure with diffusion-weighted MRI. So typically what we will do, we will have a subject entering the MRI machine, which has been presetted with a diffusion-weighted magnetic resonance imaging acquisition protocol. And then out of this, we will obtain some data that we can go and process to compute some metrics of the diffusion process, or features of the diffusion process. So for instance, these are mean diffusivity and fractional anisotropy. And I would like to go a little bit about discussing what they represent. The mean diffusivity is such that we manage to obtain an image contrast, like the one you see on the left, where a dark pixel will correspond to a slow displacement of water particles, whereas a bright pixel, like those in the ventricles, correspond to a faster displacement of water particles. In a similar manner, fractional anisotropy provides us with a tissue contrast where a dark pixel corresponds to a diffusion process that occurs in the same way along the different spatial directions, whereas a bright pixel corresponds to a displacement of water particles that follows a preferential direction. Again, we can use directional information directly in order to, for instance, color code the fractional anisotropy map of before, where now a red color corresponds to an X displacement, a green color to a displacement along the Y direction, and a blue along the Z. And this kind of directional information can really be used in order to generate, for instance, the tractography that we were talking about before. Mean diffusivity, fractional anisotropy, etc. are features of the diffusion signal decay. But what is this diffusion signal decay? So here on the left, I report the diffusion-weighted MRI acquisition protocol, and on the right, the corresponding measured signal. So we see that the protocol has some lines. The first one is the radio frequency pulses, and then the second is empty and corresponds to the diffusion gradient. And in this setup, we will measure actually the signal on the right, and especially we will go to sample what's called the echo of the signal. Now, in the case diffusion occurs in the brain tissue, we can apply a diffusion gradient and we will measure a different echo, actually an attenuated version of it. I can go back and forth with this animation so you can really notice that there is a difference here. So in diffusion MRI, we actually measure the decay of the signal that is dependent on the diffusion coefficient D, but also on the so-called B-value, which is a summary of the characteristics of the diffusion gradients we see in the acquisition protocol. We can indeed recognize the same things like the G value or the small delta or the big delta, etc. And so here we can also understand that by increasing this B value, we can reduce the signal even further according to, in first approximation, an exponential decay that is illustrated there. And this is actually one of the main things to take about the diffusion-weighted signal. It is about decay. So what we want to measure is really a decay, and then from this, measure the corresponding features of such decay. So the issue here we want to tackle is that this measured decay is actually biased. So here I report some plots, and the blue one corresponds to the true signal decay as a function of the B value that we just discussed. However, when we go to measure, we obtain some noisy samples, and these provide us with an overestimation of the true signal. And so the difference between this overestimated signal and the true one is actually called noise floor. So here we want to go to perform a procedure called phase correction that actually allows us to restore and recover the blue signal rather than just the red one. So in order to do so, we have to remember that a diffusion-weighted image is actually a complex valued image and is corrupted by what is called the Gaussian noise. So on the left, I report the real and imaginary part of the diffusion-weighted image, a DWI, which for a specific pixel, or actually voxel position P, can be represented as the sum of the true intensity A plus noise realization that has been extracted by a Gaussian distribution with a zero mean and a variance sigma squared. So now we can see that these images on the left are not really intelligible. So what's typically done is to compute their magnitude. And to do so, we actually calculate the absolute value of it. Now we can already understand that if, for instance, due to noise, we were having some negative signal samples, then by taking the absolute value, we will make them positive. And this is just a sign of the bias we are introducing. Indeed, if we were to focus ourselves on the dark area in the magnitude image M, which corresponds more or less to the ventricles, and then take an histogram of the signal intensity there, we will see actually the green histogram on the right. Whereas the true histogram will be the one colored in red, corresponding to the DWI. So the difference between the mean of these two histograms are actually a sign of the Rician bias that we want to actually remove. And for doing so, we will go to perform phase correction. So how actually do we preserve the Gaussian zero mean noise? Well, on the left again, I report the real and imaginary component of a diffusion-weighted image, and as we said, they are corrupted by Gaussian zero mean noise. And as we saw before, in order to make them intelligible and usable for our further processing, we typically perform what is called the Euler representation into a magnitude and phase image, where, as we said, the magnitude is Rician. What we could do actually instead is to perform a phase correction, where we will end up having a new pair of real and imaginary images, where now the real image contains all the tissue contrast, whereas the imaginary image only contains noise. And now we need to remember that in this case, we will have still preserved the Gaussian distribution of the noise. It's important now to say that we can perform this procedure just because we can consider the diffusion signal to be positive. Indeed, what we are going to do now is actually similar to when we use the Euler representation. We will discard the phase. Here we will discard the imaginary image because brings no information. So let's focus on how to perform phase correction. So on the left we see the original complex valued image I0, and on the right we see the phase correction procedure, where we notice that the phase corrected image IPC is actually obtained through complex rotation, where we recognize the absolute value of the original image, and in the argument the difference between the original phase and an estimation of the phase. And this estimation is really an attempt we do in order to obtain the ground truth unknown phase of the whole image. So I highlighted that in red because this is actually really the core of the phase correction procedure. So we need to have a good estimation of the phase. And in order to do so, we first start by having a regularized image and then calculate its phase. So in order to do the regularization, we define this operator rho, which is a function of I0 and lambda. And this lambda is actually regulating the weights of the data fidelity term on the left and the regularization term on the right. And once we have obtained this regularized image, then we can go and calculate its phase and use it to perform the phase correction procedure. However, this phase correction procedure is really dependent on the choice of this lambda parameter. So here I illustrate some histograms of the computed mean diffusivity for three different data sets. The first one is the red one, which is the Gaussian data set that is used as a reference. Here we can control the whole setup because this is simulated data. The second one is the green one, corresponding to the original magnitude image. And the third one is the blue, which corresponds to the phase corrected real data. And in this case, it corresponds to a regularization of 5 that is indicated there in the equation. And I want to show you how this number, especially by decreasing it, is going to change the distribution of the blue histogram indeed, and going to overlap on top of the red one. So indeed, that's what is happening. And we can slowly actually approach the reference target distribution. However, on the other hand, this slide is telling us that we really need to be careful when we choose this regularization amount, because we can achieve at best a suboptimal regularization and a suboptimal unbiasing of actually our diffusion metrics like the mean diffusivity. So a more careful look reveals the need for automatic regularization. So again, on the left, we see the polar version of a DWI. And by applying a low value of lambda, we will obtain a very smooth phase estimation. On the contrary, when we have a very high value of lambda, the phase look pretty much like the original one. So we want to really have something in between and find the optimal value of lambda. And indeed, this is even more true when we keep in mind that in order to perform phase correction, we will discard at the end the imaginary component. And in the first case on top, we want to be able to do that because we have actually some tissue contrast in the imaginary component that we will discard later on. So how do we find this automatic regularization? Well, the idea here is to use noise information. What we propose is actually to measure noise information directly from the MRI machine. And here I repropose some parts of the acquisition protocol, where in a typical scenario like this, at the echo, we will be measuring a complex value diffusion-weighted image, or if we applied, of course, the diffusion gradients. However, this is just the result that we obtain by applying the radio frequency pulses. So the idea is to avoid using such pulses, and in an ideal scenario, by doing so, we will be measuring a zero-valued image everywhere. Instead, when we do so, we are actually sampling a single noise realization of the thermal noise coming from the whole reconstruction pipeline within the MRI machine. So the idea here is really to use this noise realization in order to infer the noise variance of the images, and to use it to perform an automatic regularization like we show before, and I'm going to detail just next. So the idea is to use noise information to create an adaptive regularization. So as I anticipated, on the left, we see that we use those images collected with the method described before to calculate locally the variance of the noise. And with this variance, we can actually compute a weighting function called W. And this weighting function is actually used to be sensitive to the variation of the noise locally throughout the image. And so this is a first use of these noise maps we have just acquired before. However, we are still left with the problem of determining what is the value of lambda. So typically, what's done often is to use the discrepancy principle, which states that we need to find the value of lambda that minimizes the formula you see on the right. The formula you see on the right is actually the difference between the measured noise variance sigma squared and the residuals corresponding to our the application of our operator with a specific value of lambda. However, several authors have been pointing out that this is suboptimal and can lead to over-regularization. So the idea was to propose something more sophisticated and to use what's called the Stein's unbiased risk estimate, or SURE. So here we distinguish again exactly the same formula as before, but we are going to add another term where actually some divergences of the operators appear. I'm not going to go into details with that, but I want to show actually how this can be estimated. And this indeed can be estimated in this way, where we apply a formula that depends on bxy, which is a vector, and of course depends on the operator itself that we have been using, so a rho. And in this case, this bxy is an image of the same size of actually the images that we want to process, which entries are drawn from an identically distributed zero mean Gaussian. And so through this procedure, we can actually really evaluate the formula that we see on top. And this is known as Monte Carlo SURE. However, this formula does not take into account the fact that noise varies spatially. Therefore, we need to do something different and take into account the spatial variability and to come up with something called spatially varying Schur, SV Schur. So here I illustrate some examples of how the noise variance varies throughout the image. And there are some values called Q there that represent the degree of spread or concentration of this variation in the image. So in order to tackle such a situation, then we need to find a different way of how to estimate the divergence terms that we have seen in the formula above. And the way we came up with was to compute a different vector bxy that we call the SV because it's spatially varying. Then now we can replace to the original formula and then go back to really evaluate this Schur in a spatially varying scenario. So here I want to illustrate a little bit the comparison between the standard version of Schur and its spatially varying counterpart we came up with. In this graph, we see some black lines corresponding to the mean square error between the original ground truth image and the one we can actually obtain through our operator, through our regularization setup. And of course, in a real case scenario, these black lines will not be known a priori, but here we can know them because this is a result of a simulation. What Schur really does is actually providing us with an approximation of those black lines. And then, of course, in an ideal scenario, we would like to find the value of lambda that is on the x-axis that minimizes the mean square error. And because we only are provided with, thanks to Schur, to an approximation or an estimation of it, we would like to compute these colored lines with the crosses there and then find their minimum in such a way that we can actually be almost certain that the minimum corresponds also to the minimum of the unknown mean square error function. However, we see here that the red dots corresponding to our attempts of estimating the minimum of the colored curves do not correspond to the ideal or to the optimal lambda of the unknown black curves. And this was really the reason why we needed to move to a spatially varying version of Schur, where now we see that the attempts actually are much closer to the optimal value of lambda. So now that we are equipped with these tools for regularization and these ways of estimating the noise variance, then we can really actually go and perform what we called adaptive phase correction. So here on the left, we see the magnitude original image, and then in the middle, in the top row, what we call stationary phase correction, where we didn't consider that the noise was actually varying locally. And in the third column, we see the adaptive phase correction. Below, we actually see the differences between each pair of images. We can already see that adaptive phase correction indeed can change the tissue contrast much more compared to the stationary. And in order to better indeed appreciate the differences between all of the three type of images, we can compute the histograms in the ventricle area where the signal is actually low. And in such a way, we can really observe that the magnitude image, as predicted, only contains positive signal intensities, whereas the adaptive phase correction histogram in blue is providing a Gaussian shape and also negative intensity. the stationary version of phase correction indeed provide us with an histogram that is in between the two. So another important thing to do in such a case is to check whether we are inducing distortions in the transformed images. Indeed, we need to remember that we are actually transforming the tissue contrast by performing this adaptive phase correction. And one way to check that we are doing things correctly is by checking the number of outliers that we obtain in the images after performing this procedure. So an outlier is detected when the difference between the original magnitude image and a phase corrected real version exceed twice the noise standard deviation that, of course, we could know thanks to the acquisition of those noise maps we have seen before. So here, the different rows represent different ways of deciding and choosing the value of lambda. And the last one corresponds to this adaptive phase correction procedure that I've been discussing, with the use also of the spatially varying Shor criterion. The other two are just lambda values that have been selected by looking at the images in a heuristic way. And on the columns, we see the different B values we have been applying in, actually, this is a real data set. So we see actually that adaptive phase correction reduces a lot the amount of outliers compared to when we just choose in a heuristic way the regularization amount to use. And also another thing we can observe is that this adaptive phase correction really provides an adaptive behavior in the way it performs the correction. So I would like to focus your attention on the plot below on the right, which we have seen at the beginning. And actually, we notice that the difference between the blue and the red lines increase with the b-value. So indeed, we would expect that similarly, the correction we are going to perform on the images also mimics this trend, and it should be very little when the b-value is low, and it should be larger when the b-value is large. So in these images, I plot the amount of correction performed in average by adaptive phase correction on the left and by a competing technique, which is a Gaussian filtering type of technique on the right. And we really see that in the case of non-weighted images, so when the b-value is equal to 0, adaptive phase correction can really perform almost zero correction on the signal, whereas that's not the case for the competing technique. Moreover, as we increase the b-value that you see reported on the left, we see that adaptive phase correction produces a stronger and stronger correction, as we actually should expect. And finally, with these phase-corrected images, we can also go and compute some of the metrics we were discussing at the beginning, such as mean diffusivity, fractional isotropy, etc. So here I'm illustrating a different one called axial diffusivity, which is, instead of being the average diffusivity detected inside a voxel, is the highest diffusivity detected in a voxel. So we see here along the rows that the b-value is increasing. And again, we see the percentage change compared to when we use magnitude images that is increasing as the function of the b-value. So here in the color bar, a value of 0.04 represents about a 4% change, and in this case, increase of the actual diffusivity value after adaptive phase correction compared to the case when we use magnitude images. And similarly, on the right, there is the competing technique that does not show such behavior. Moreover, we can compute multi-shell indices, which are a different type of diffusion metrics that are typically computed, such as mean kurtosis MK or mean square displacement and return to origin probability. And also in these cases, we see changes compared to when we use magnitude images. So in summary, the take-home messages of this presentation should be that by acquiring complex diffusion-weighted images, we can actually perform phase correction, and that the phase-corrected DWIs can, however, present distortions. So the amount of outliers is if the phase actually is poorly estimated. And then also, here we showed that noise information can be used to obtain an optimal phase correction, and that this noise information can actually be directly acquired as additional data from the MRI scanner. And finally, that by using noise information and dedicated regularization methods, it is possible to obtain an adaptive phase correction that minimizes the distortions, so the outliers, while at the same time preserving the Gaussian distribution of the images that is very good for computing the diffusion metrics like mean diffusivity, fractional isotropy, and the others I've been discussing before. Finally, I would like to remind you that the article is present as this reference, and there is also the code for performing adaptive phase correction at that GitHub address. This work was funded by the European Research Council ERC under the European Union Horizon 2020 Research and Innovation Program, CoBCoM Computational Brain Connectivity Mapping. Thank you for your attention.